My name is Zoe Conroy. I will be the moderator for the next session here, the panel. And for the panel title, we chose, Will Successful Chiplet Integration Only Happen with Testing Coopetition? And we really have an esteemed panel here today of industry experts. And I'd like to introduce the 6 panelists. Erik-Jan Marinesian, he's director at IMEC. Sridhar C.R. is principal engineer at Intel. Phil Nigh is in test engineering at Broadcom. Al Yanes is chairman of the PCI SIG group and is also a distinguished engineer at IBM. Dave Armstrong is principal test strategist at Advantest, and George Harris is VP of Global Test Services at Amcor. And we had some discussion around what the title for this panel should be, and we really like this word coopetition. Because the definition goes back to collaboration between business competitors in the hope of mutually beneficial results. And we felt that in regards to chiplets and this whole HI integration, where you're having multiple companies, potentially even competitors, putting chips together on a single interposer, that we really truly need cooperation between all parties here, and that this word was very apt. So with that, let me just discuss the format briefly. Each panelist will talk for a few minutes on just a little bit on their background, their career, and a little bit on their stance on the panel title here. And then we will go into some general questions, some pre-questions that we have here, and then we're going to open the questions up to the floor. And with that, I'm going to I will stop sharing, and Erik-Jan will just share his slides and his stance to start with. Erik.
So I gave the following, like an alternative version of this panel title to my presentation. That is test competition a requirement for chiplet integration. It's kind of the same as what the panel is. So this is me. Joey actually asked to include one bio slide, so here you are. I most of the time work for IMEC, but one day we also have an affiliation to university, and sometimes I teach courses. And this is where I used to be, NXP Philips, and blah, blah, blah. There's also more in my bio, right? So I need to hurry up. So read this at home, I would say, when we make the slides available. So first, I have agreed with Joey that I could go first, because actually I have an interesting take on this word competition, right? Cooperation between competitors. Let me tell you what we do at IMEC. At IMEC, we are the world's leading R&D center for nanoelectronics and digital technology. We work with companies, startups, universities. Many of the leading semiconductor companies are our customers. We call them partners, right? And also we work with many of the suppliers to this industry. That is basically equipment suppliers, material suppliers, as well as EDA software tool suppliers, for example. And there you see revenue headquarters in Belgium, offices in multiple continents. Actually, if you look at what we have, what are our 2 most important resources, then it's what the marketing department calls brilliant minds, right? We have like 5,000 of those. That includes, of course, a big portion of IMEC staff, like myself. Also many industrial residents, people from the company that we partner with, and they work together. They maybe come from the mothership down to Leuven and work with us for like a couple of years, and then maybe go back, right, taking the knowledge back. We also have about 800 PhD students that are our junior employees, let's say. Postdocs, and so next to the staff we also have 3 wave fab, right? We used to call them 200 and 300 millimeter. Then when we start a 450 millimeter fab, and when in the end the 450 millimeter equipment did not really materialize, then that also became a 300 millimeter fab, and now we call them just fab 1, 2, and 3. Good. So why is IMEC so special? Because we're a company, but our product is research, right? And actually it's research based on cooperation between competitors as a business, right? And I will show you in a few slides that we really do this as a very successful business. So, Joey had asked, do we have an example of competition that is successful? Yes, I have. That is actually the place where I work. Now, the topic of the research is then basically pre-competitive technology R&D, right? So, of course, later we'll be talking about test competition. Maybe that is something else, but at least from the technology R&D, it's very good to work together. Here, for example, you see the ASML extreme ultraviolet wafer stepper, right? This is the first one, and was here at IMEC, and and we made it to work. Of course, now it's already in production in various fabs. But so at the time we had like 100 people from ASML, permanently at IMEC to make it up and running in our clean rooms. So the topics that we work on are always mainly technology driven, right? Memories, logic, both, let's say the really hardcore technology on how to produce transistors, as well as the design impact, lithography, interconnect back-end of line, 3D, silicon photonics, high security, quantum computers, machine learning, all these things, right? You see a picture of one of our fabs, this is Fab 2, I think, yeah. And so all these fabs are, you could say, fully flat, 300 to 200 millimeter R&D pipelines. The total investment is quite some billions. There's then the investment typically in the building, etc. But a lot of these tools actually are first of a kind prototypes that maybe we co-developed together with the supplier of that equipment. He or she then, like the ASML machine, puts it in our fab, and of course, we have to debug it, but later we get to keep it, and then, maybe for a very reduced price or for free. Or if you want to look at our fab, you can do a virtual tour of Fab 2 in the cleanroom app that you can download on your cell phone, as I have that too. For information, tailoring it a little bit to test. My supply partners in test are these companies, right? These companies that I've worked with in the past and that we have some equipment from or software from. Now, here, actually, these names here are a little bit outdated, but I think these were the partners that we had in 2017. And but I could not find newer slides, and I don't have all the information. But these then are our IDM and foundry partners that we work together with, right? And most of these people have really a whole team also of engineers on site. So there's the team of TSMC on site with the local engineering manager from TSMC on site, blah blah blah. And that is true for all these. You might see that there is a lot of competitors here, right? For example, all the Samsung, Micron, and SK Hynix, of course, are all three DRAM manufacturers, big competitors with products, but in the technology, pre-competitive technology development, they're working together. That makes a lot of sense, because of course the pre-competitive technology development can be quite expensive, and so that makes sense that they then share the cost to that, right? Here you also have some maybe more fabless and fab-light partners that we work together with. And if we zoom in then, let's look here at the supplier partners. Again, this might not be the full exhaustive list today, but it was true in 2017. That's a large list, right? And then actually we also work together with application partners, and that is even a larger list. And you might even notice that some of these companies are both on the top and the bottom of the list. And mind you, these are not people that we just once meet in a bar, right? We have all cooperation contracts with all of these companies. So and there's a lot of competitors in there. So you could say, this is, if you do this successfully, then apparently you have competition working, right? So now I have two slides on this. So IMEC is the definition, you would say, of competition. And let me first look at the scientific success. Well, I just took 2 comments about ISCC and look at the number of papers per company per year at ISCC. The green line is IMEC, and so the others are several other of our customers or other companies. You see that IMEC is doing pretty well. Right? They're at the number 3 currently, just after Samsung and Intel. And I think of course Samsung and Intel are a lot bigger than IMEC is. And IRPS, maybe tailoring it a little bit more to testing. It is actually the reliability physics symposium, right? So it's more reliability, which of course is, if you do technology development, then we don't do so much in testing, but more in reliability, and there we're absolutely the number 1, and we dominate that conference. So I would say scientific success, and these are not just. There's many more conferences where you can show these type of charts on. Right? And then let's look at the business success. Well, currently we have this is 2020, the latest number that I could find. We have 6, 7, 8 million euros revenue. There's a profit and loss. And if we divide it over where it comes from, there's a small part, it's not even 25% of the total. It's a little bit more than 25% in total. That is government funding and EU programs, of course, where we also participate in. But most of the money really comes from industry, because we have to earn our money by working for paying customers, right? And that might also be different from other research institutes that you might know. For example, in Germany we have doesn't enter my mind. And we have CLET in France, right? We have ITRI in Taiwan. Fraunhofer, of course, in Germany. We have Fraunhofer in Germany. But they get most of the money from subsidies and so work for a very local industry. Now, the fact that we are independent makes that we have to work for everyone, right? And it would not make sense that the Flemish or the Belgian government would pay the research that we're doing for Samsung or Intel. That then pay them their own research, right? So I just want to show this that IMEC, I think, is a good example of the definition of competition, but not in testing, right? So now let's move to. So I agreed with Joey that this was my introduction on competition. But now I will talk about the topic of the panel. Is test competition necessary for successful chiplet integration, right? So let's look at systems built from multiple components. We had, of course, printed circuit boards, system on chip. And now, the whole thing is 3D stacked ICs, right? Or heterogeneous integration, or whatever you want to call it. But if you look at that, of course, why we're doing this, we're all doing it to get fast development to modular design, right? Of course, we could all make our own memories, but before the time that you have your memory factories running, it's better to buy from one of the DRAM vendors memory. And the same is true for logic and etc. So it makes fast development to modular design. But these modular designs, I think, then you also want to do modular testing for, right? Later, in a few slides down the road, I will just argue that you can only do good, proper testing for manufacturing defects if you know what is inside. So that means that I think the guy or the company who makes the component should also make the test for that component. Only he knows what is inside, because the integrator and the customer wants to abstract from that. That is the whole reason for doing modular design. So if you want to do modular testing, also known as hierarchical testing, you should have some kind of wrapper. This wrapper DFT defined that allows to do in-test and X-test, and that meaning that you can test the model in the in-test mode as a standalone component, and to require, of course, access to via test access mechanisms from the chip pins or from the board interconnects or from the package pins to whatever module you're going to test at that particular moment. And if you have, and that is of course always the case, if you have multiple components onto a system, then you have to make sure that you have interoperability between these multiple components, and that then of course requires standardization. Otherwise, you get this effect that everybody builds his own working thing, but together they don't work. Now let's look at the black box testing. That's also one of the questions of Zoe. So I'm not a fan of black box testing. Let me explain you why. There are some universally true principles, I think. Design verification is not the same as test for manufacturing defects, right? So here, of course, design verification is something necessary. Design verification, I think, is something similar. Black box testing is something similar as functional testing. It's something similar as design verification, is something similar as system level testing. Now, it's all useful, right? But it's not good. It's not the same, and it's not good enough for manufacturing defects. If you want to do thorough testing for manufacturing defects, it should be there, not manufacturing tests, then you should be aware of the implementation of the thing that you're testing, right? Look, for example, at this whole movement of cellular tests in the ABG world for digital logic tests, where you see that even if you know what is inside your AND gate or your OR gate, you can get a better test, right? So let's not say that you can test a microprocessor by not knowing what is inside the microprocessor. You have to know even what is inside the AND and OR gates for good testing. Now, the other universally true principle is, of course, the test for manufacturing defects can only take place after you have done the manufacturing of the thing you want to test, right? You can, of course, develop the test prior to the manufacturing. There's no problem. You can develop a test based on the design only. But the actual execution of the test can only be after manufacturing. Now, what does that mean, right? That means that the test responsibilities follow the manufacturing flow, right? So let's look at the different manufacturing flows. And here, I take very coarse look at the manufacturing flows. So I just make a difference between the component provider, the supplier, and the integrator, the customer of that supplier who makes it into one system, right? So here we have the suppliers. In the printed circuit board, for example, we get bare boards and we have packaged ICs. And the integrator then needs to solder them onto the board. So then, you can test for interconnection, you have systems. Now, what I'm going to show here is four different colors: design, test development. So that is both light colors, meaning they're still before you have anything really solid in hand, right? Just on your workstation. And then we have manufacturing and test execution. So you see, there's two ways how we look at these colors. You can look at the light colors, that is before you have something real, and the darker colors when you have something made. And you have yellow and green, right? Yellow being on the make side and green being on the test side. So we would have something like this, right? If you make a system, the system guy, says, okay, I want to have these and these chips, so they need the package, the chip suppliers need to design their chips, make a test for them. So here you see that all the manufacturing almost takes all place, on the top side, right? And the integrator only needs to solder them on the board, the chips on the board, and do some interconnect testing. And that's of course different here, right? Because actually these cores in the 2D system on chip, they're being designed, they're being tested, maybe on the specification of the system provider. But this guy, he doesn't make anything, right? So as he doesn't make anything, the testing can only happen here, because only here these cores are part of a larger SoC already being manufactured. So you could wonder if I say test development here, what is then test development here still doing? This test development here is an interesting test. That will be hierarchical testing, right? There we go. So that means that these tests, one test or multiple tests per course, will be units that we will be working to a hierarchical test. That maybe these component tests, for example, need to be expanded to the chip level, right? So finally you can test them. And so there is, here's an extra call, right? The hierarchical testing. So those may be different. And that is why you need wrappers, and that is why you need test access mechanisms. And so here, here is again similar. Because here we have also these dies, they're already manufactured here, so these dies can be tested by their suppliers before they're being put in the stack. But then it's still necessary probably to do hierarchical testing, because the stacking done by the integrator is done under thermal compression, higher temperatures, some force. That means that this could be damaging to the die, for example. So typically after integration, you still want to test it, right? Here we're talking about pre-bond testing, and here we have mid-bond and post-bond testing. So the mid-bond and post-bond testing, then of course you need also this hierarchical testing to be able to execute the test from whatever it is in the package frame. And that exactly in that domain is where standardization also plays a role. Now let's look at it. We have 3 standards. Each of these types of service has an IEEE standard, right? Because IEEE typically is the home of our DFT standards. So they have standards for wrappers and test access. LAN 4.9.1, 1500, and now the new standard 1838, right? Here in the table, I'm not going to talk about all the details of this table, but I have the 3 standards listed out and kind of where they are equal or different. You might see that apparently every 14 years we release another standard, right? So my prediction is that in the 2033 there will be a new standard, and whatever that will be. But I will be retired by that time. So and here, I call it a little bit. This is then typical for JTAG, right? Where we have a 1x1 interface. Here we have typical for 1500, where we have other things. And here we have kind of this new standard. We have kind of played. We borrowed from both the blue side and the yellow side, and also some things which are really new to 1838, which are then green in this case, right? Now let me give you one slide summary of what is 1838, the new standard. So it's a standard that specifies mandatory and optional 3D features per die. So here you have a die, let's say. I don't know what it is, but some functional die. What we put on is all this colored stuff. So we have die wrapper registers. So that's the wrapper to make sure that we can put the die as standalone unit, and also the interconnects as standalone units. The control mechanism, of course, to give the right instructions to make the die do what we want it to do in a certain test mode. And a flexible parallel port, because if you have to test everything to a single bit in, single bit out, it might take forever. And so the flexible parallel port gives you more bandwidth. And if then you have more of these dies, you can just stack them on top of each other, and you should have a certain minimum amount of consistency in the test architecture. If these dies indeed are compliant, such that if you have here your nice AT and you connect it together, then for example, you're able, even when you're in stack, to test the top die, the middle die, and the bottom die. Standalone units, right? Now, then the last slide I have here, Zoe also had mentioned several nice to have, what I would call nice to have features. For example, design for tester. the user, the integrator, get the design for test description and the different modules? Maybe can he or she even specify what he wants to get there? Should we get access to on-chip sensors, voltage, temperature, aging sensors, whatever you have? Should we get access to design for test features still off-chip that are still available? Do some testing even though the chip is already assembled. Should we get traceability features, test data results from the suppliers, from the die suppliers and the 3D stack? Yeah, I think you can get all of these things because how to do it is known, right? Implementation is how to do this is known. And the system integrator, that's just a customer, right? So he should specify what he wants and probably pay for it also. So nothing is for free, of course, because all these things require some extra effort on the side of the supplier. So I think they are just all part of supplier customer business agreements, right? And with that, I'm just signing off. Bye-bye. And that's it. Thank you.
Okay, thanks, Eric. Jan.
Yeah, so I'm Phil Nigh, test engineer, and working on some of the leading edge multi-chip products. I did the math for this bio. Next year, I would have been doing this 40 years. When I started with IBM almost 40 years ago, I worked on a multi-chip product, had 90 chiplets on it. And when they would pass all the other tests but fail in the system, parts came back, they would pass all the tests again, then they'd give them to me. And 40 years later, I'm more or less doing the same job with, call it 2.5D advanced chiplet products. For example, I'm looking at silent data corruption fails. To pass everything, come back, we're throwing everything we can at it and trying to get as much learning as possible out of those. So next slide. And I'm going to talk to this from the Broadcom ASICs division perspective. And it's a little bit different than this coopetition view, which is for what these products, Broadcom is designing all the silicon. We do buy the HBMs from the obvious suppliers, but besides that, they're designed internally. So our goal is to design it and deliver it for the priorities of our customers, which is mainly first performance, reliable time to market, quality, and cost is, these things cost a lot. But that's our view. And it also means since we can design both the main chip, processor, SoC, and the chiplet, we aren't buying chiplets from other companies. In the future, maybe we do, maybe other Broadcom division companies do, but we don't. So we can design it in. So as far as following industry standards, we would only follow those if that made sense for our products and our customers. And that's one question about the chiplet direction in general for the industry. In 5-8 years from now, or is there going to be a category of chiplets and anybody could buy one and then the company's got to deliver it like almost a commodity? Or is it still going to be only, call it cliques or groups of suppliers where maybe the final integrator works only with 1 or 2 companies as far as getting chiplets in and not buying out of a catalog, broad catalog? And also a brief comment based on earlier presentations. When you go to hybrid copper bonding, imagine taking what Will talked about micro bump and the challenges and multiplying it by 1,000. That's some of the challenges with hybrid copper bonding. There could be 1 million signal IO connections between 2 chiplets when you go to that, and the world changes. Okay, so a couple of other comments, then I'm done, is hopefully nobody, the whole issue of known good die, known good chiplet, what does it mean? My opinion is you don't assume it means all the devices are going to work. I think I've heard rumors companies have done that before and been burned by it. The key question about known good die when you buy a chiplet is how many are going to fail next level of assembly or in the system? Give me a number. And also from an industry perspective, if you're thinking about buying chiplets, one interesting question is what information do you want with the chiplet? In other words, what DFT does it have that clearly has to be shared to apply that at the next level of assembly or in the system? You have to give you some level of traceability, at least for the kind of products that Broadcom ASICs works on. And also, the more interesting question is, what data do you get? Do you get a whole host of data about that chiplet, or do you get nothing? And I bet the standard practice today is almost nothing, except maybe a little bit of voltage or tuning stuff. And just an FYI, upper right is from about a year and a half ago. And it just shows an example of the kind of chiplets we're looking at. That one was done at 5 nanometer, a big ASIC SoC in the middle, some HBMs, and 4 or 5 other chiplets around it. So that's it, Zoe.
Okay, thank you, Phil.
Okay, good morning and good evening for folks around the world. You can read this offline. The only thing I'll point out here is that, I have been deeply involved with interconnect testing. So my discussion would be, a little biased towards that. I also work in other areas like silent data error, functional safety, and the silicon lifecycle management. Maybe you can move to the next slide. Okay, so, the previous speakers, and actually even yesterday and today, there are, a lot of speakers have spoken about, how we can do independent testing of the die, things like that. And I think those are very well taken. The industry is looking into that. It is not a new problem, and the challenges are there. What I will do is that I will focus myself a little, my focus would be a little more narrower. Once we have the dielets or the chiplets, we have to interconnect them. Every company, has its own way of interconnecting them. And let us for a moment focus just on that little piece and see that what is coming down the pipe. We have been in Intel designing our own chiplets and connecting them and putting products out in the market. For those of you who follow Intel's products, things like in the HPC market, we already have products that are integrating, 40 plus dies, and I can see this is only going to go up. The number of interconnects are going to be very high. In that product itself, it is close to 100,000 interconnects. Speeds are upwards of 3 gigahertz. And for future products, it is going to get worse and worse. Okay. And what we are seeing from silicon is that there are some complicated failure mechanisms. I just put in a few examples there. We see a lot of failures across signal lines, and not only between 2 adjacent ones, but across multiple lines. Okay, and then this goes on from the signal lines to the clock lines. So all of those pose a challenge. We also see significant coupling effect. Okay, so all of this suggests to me, and it is a point that actually Eric made, okay, is that we cannot be talking about SLT test for these interconnects. We need to understand the defect mechanism. And in my opinion, we probably need specialized tests for these kind of interconnects. And the important thing is that once we start going down that path, both sides of the die has to support that and understand that. Okay, so that is really the most important thing. We need a simple pass-fail test, defect-oriented, whatever be the test. And we need to also do, and then if you go down the list of other test features that are required, for example, for diagnosis, we really need a non-destructive means. That means, we have to be able to run some kind of tests and identify the fault location. And here by the fault location, we are not talking about which location within a die, but we, as a start, we need to know whether it is in any one of the 2 dies or which die, or is it in the interconnect. Given the reliability of these interconnects and the complex process that we use to manufacture them, interconnect repair is a requirement. Okay, And because there are so many large numbers of them, they are distributed all across the die. We cannot do tester-based repair. Okay, so we really need some kind of on-die repair mechanism that is very analog to what we do for array test and repair. Okay, and if you go further down, right, there has been talk about system-level tests. Our OEMs are asking us for hooks so that they can run these tests to make sure that the dies are interconnect and those interconnects are working properly, and before they actually run the rest of the test. Okay, clocking is quite tricky. I am seeing a lot of variety of clocking methods being used, and so we need hooks into that. And going down the road, because of the availability and aging-related failures, there is a requirement coming down the pipe for in-field test and repair. So if I put all of these things together, we really need to be able to work together to solve these problems and support these features. And without that, I do not see how we can actually solve this problem. So long it is contained to one company, yes, we can come up with custom solutions. That's great. But once we start, for economic reasons, start integrating heterogeneous dies from different companies, I think we need to start talking to each other and co-op. I don't see any way out of that. Next file, please. Okay, so in my opinion, co-op, there's no file. There's a build there. Yeah, sorry, there is a build there. Yeah. So we can just do the build.
Yes.
And then the next one is, coopetition is a necessity. Intel has started on one with a lot of our partner, competitors actually. So I think that is the way forward, and I don't see anything, any other way out of it. So that's really my pitch for this.
Thank you.
Yeah, thanks.
Yeah, thank you, Sridhar.
When I hear about coopetition, I think of standards. And we in the PCI SIG, we've been in the standards business for about 30 years. We've been pretty successful. We're developing the PCI Express technology. And as you can see from our board of directors, there are a lot of competitors. And we managed to cooperate and sort of keep the politics down to a minimum and focus on the technical solutions. So I'm going to highlight a couple of the recipes that have made us successful. And, if this coopetition goes down the standards path, maybe these will be seeds for enabling that. So one of the recipes for our success is it's a flat member fee. There isn't any tiered membership. So everybody's on the same level playing field. And I think that helps from access to the specification. The flat membership fee also, or the flat membership structure also applies to the board of directors. So it's a very open standard or consortium. The board of directors get elected every year. Any member can participate in the work groups. We hold free developers conferences every year. We also do compliance to make sure things are interoperating between our members and between a sort of a gold standard. And just from our particular solution for PCI Express, we've maintained backward compatibility for many years, so that allows folks to develop their products, adding cards independently of the motherboards. So that's important for us. Yeah, so some of the way we interact within the organization, we follow Robert's Rules of Orders for meetings. We do 2/3 majority. This ensures that you have enough of attendance and a quorum. So just you need structure to enable standards and to ensure that things are being done, well and sort of open. From a development perspective for specifications, we do a 5-step process. So there is a continuous feedback to all our members, seeing the specification before it gets released. So this allows, folks that are not part of the work group to have access to it, and you don't want to wait until the end. to release your specification so you make sure that everybody's in sync and everybody's providing feedback through the process. The third one's very important, obviously, the IP policy. So we follow RAND, which is a reciprocal and non-discriminatory policy. This ensures that if somebody puts an IP into the specification, that they must share it at reasonable cost to all the members. So this allows folks to freely share their IP, and there's a sort of a you can't lock somebody out or charge a high price for the IP. So this is essential in my mind for doing successful standards. Obviously, it's an organization that you need an administration. You need to have somebody with good financials and bookkeeping. For us, like I mentioned earlier, to minimize the politics and the business parts of things, we focus primarily on the specification and education. We don't want to get into politics because that takes away from developing the technology. And as I mentioned before, it's an organization. You need to run it, so you need to monitor the financials and making sure that the organization is going to be financially successful besides just the technology success. So anyway, these are some of the recipes that we've used over the last 30 years with PCI Express. So maybe food for thought for those that if this goes down to the standards path.
Yeah, thanks, Al. Yeah, I definitely would like to have a few questions on standards a little later.
My background's a little unique. I have certainly a lot of well, first off, I'm a principal test strategist at Advantest, which means I work with both customers and R&D. I also work in a lot of industry efforts. So I have decades of experience in testing the leading edge products. And in my ITRS HIR effort, I've coordinated and led the roadmap committee for a very long time in what is called pre-competitive collaboration. And frankly, it's not easy to manage, but I believe it has been successful. Before going on to the next slide, my first knee-jerk reaction, I think, was similar to some of the previous presentations, and that is, why do I need Teradyne? Sorry, Ken, couldn't resist. But the reality is, Advantest should be able to do it all, right? And let me challenge that a little bit, or add some fuel to that philosophy. Next slide, please, Zoe. So this is the definition, and we've talked about this. Click, please. It's illegal for some co-opetition. If you write anything down, if you talk about, hey, this is what we're going to do, you can actually be prosecuted. However, if we can benefit customers and we can look at it from the big picture, we can do it. And obviously there's examples where it can be done. And here is a key example just announced earlier this month. Consortium of efforts involving TSMC, Samsung, and others. Obviously they're competitors, Intel. So obviously it can be done. And, I think we need to look seriously at this. So it's a challenge. And I think certainly Teradyne and Advantest have worked together very successfully over the years in lots of different areas. So let's talk about some of those areas. Next slide, please, Zoe. So opportunities, test patterns. We got multiple patterns, file formats. Why don't we focus on one? It should be easy for us to do. And the value, I think, would be really high for the industry. One translator for my product and Ken's product would make sense. What about the files behind it, the level setups, the timing setups, etc.? Can we actually leverage those? I think it's easy, sure. Now, this is where it gets a little more dicey. What about geometries? Can we standardize on pitches and probe placements and files to manage that? Can we standardize on data highways? You know, we need to be able to share data, and obviously we got to share data well beyond the tester. Can we do that? What about actually the test floor, the WIP management, tracking mechanisms, maintenance routines? All of these seem like green opportunities for me. Next slide, or next click. Some are difficult. Maybe I should have used yellow, but it wouldn't have shown up. Security protocols, I think, are difficult. Timing definitions are difficult because architectures are different between the various test platforms, but it doesn't mean it's not impossible. Fault coverage models and metrics, please. Let's try and figure out a way of working this and getting better understanding of what we're covering where. This is a challenge for all of us. I think some things are impossible. I think a DUT layout and probe configurations are, I think, very, very difficult. And I don't think, you know, I've seen blogs recently on, you know, this product or that product. You know, what if we think about a chiplet as like a TTL data sheet? You know, will we have a blog in the future which says, hey, I used the, what was it, a 1N, 2N, 2222 or whatever, this chip to, and it didn't really meet its VIL spec. I don't think that will occur. So here's the spectrum. Green stuff, let's work on. Red stuff, maybe. Black stuff, let's forget. Back to you, Zoe.
Thanks, Dave.
Okay. All right. Well, thank you. Pretty exciting so far. You can go to the next slide. Just brief overview for me. 32 years in the industry so far. It looks like from Phil's discussion about approaching 40, I'm chasing him, but he keeps going. So I hold a few patents in many different areas. And I joined Amcor in about 2020 as vice president of the global test services business. Just a few quick facts about Amcor. Founded in 1968, significant footprint of manufacturing space, 11 countries. We just announced our new assembly and test facility. We broke ground in Vietnam. About 30,000 plus employees. We service most end markets. And from the test perspective, we have almost $1 billion business for our customers here. Thank you. If you go to the next slide. Heterogeneous integration testability, we've talked about a lot. Of course, our main topic here is coopetition. And as you've seen from several of the panelists that have spoken already, it's already happening. The observability and stimulus capability within the SIPs and the chiplets for test engineers, they're needed, whether Amcor is doing the test solution or we're accepting a test solution from others, or we're co-developing a test solution between our customers, and those customers might have chiplets inside that are from different vendors. So that coopetition, that collaboration is already happening. And I think we're going to get into most of the, we have already some of the challenges that are ahead of us. So I think I'll take my 3 minutes, and that's probably it, Zoe.
Thank you.
Dave, I'll jump in. I mean, if we're like buying chiplets from the same supplier, that's the ideal place to collaborate. For example, the HBM standard JESD 235 doesn't cover everything, but I think it was put together, I think 9 years ago. It was released, and it does a nice job of describing a lot of test stuff. Not all the details, and it's not perfect, but it's pretty good. And that's the kind of that to me ought to be used as the model of call it a success story.
So would you be willing to share some of those fringe use cases with Intel and try and grow the effective spec?
I've been somebody for, and I hate to keep dating myself, but a long time. 25 years ago, we formed a group with Intel, IBM, TI, at that time, a couple other companies, later LSI, Avago, where we would get together on the side and share horror stories, share best practices. So simple answer is yes, if the kind of the format and structure all makes sense, but it may not be a broad industry-wide standard or collaboration where anybody, it might be something. My view always was people would share more if the crowd was smaller.
Makes sense. Anybody else have an opinion? Or
yeah, maybe I can add to that. We are already working. I'm from Intel. We already work with TSMC. We don't disclose the processing, the competitive packaging technology we have, but on the design end, the hooks that are needed, they are openly shared. TSMC is not that interested in that. We are, but it is available to them. So I think, if you start looking at standards that you can build into the design, I think that's the way to go. We don't need to disclose, the details of the processing, which is basically our competitive edge, right?
So on the subject of standards, clearly there are some standards out there, but a lot is not standardized with the chiplets. It's sort of the Wild West in terms of what you're going to get. I think, Sridhar, you mentioned that we're up to many thousands, hundreds of thousands of interconnects. Yeah, so it's highly complex with this connectivity, and then we're running at high speeds. Do you think the industry as a whole should be looking to standardize anything around chiplets?
I think so. I think that is the way to go. I think, for example, I looked at the 1838, and there is a mention of it, but what would be good would be to see how that standard can be used. We can list out the kind of features we need. Some of it I listed, others can list others that they see coming down the pipe. And I think we should all get together, and whether it is 1838 or some variant of that, we should say that, how can we build those features into the standard, support those features? Everybody, and that would be the standard, right?
Yeah.
So Sridhar, are you then referring to the redundancy features? That's what you're saying, right? Or the repair features?
Everything, right? Not only redundancy, do we need specialized tests? Do we need repair? Do we need support for system tests? Do we need support for the clocking? We can agree on what are the main things, right? I just listed some of them, right? And I think it would be good to articulate in the 1838 how these features can be implemented within the standards, or if you have to evolve the standards, let's do so.
Do you think 1838 should be sort of have the next revision of that, or would you look at a completely new standard being defined?
Well, in my personal opinion, yes, maybe a new standard, but but that's a logistics problem, right? Whether we have it within 1838 or we have a separate one, it really doesn't matter. So long there is a well-articulated document somewhere which we can all agree on, or at least most of us can agree on, I think that would be the way to go. Yeah.
I wanted to address some of Dave's concerns, and I also want to mention that within the PCI SIG, we do have an antitrust wording that we don't talk about price. So I think it's important, if you go down the standard approach, you don't talk about business. You talk about technology and technical stuff. You stay away from business deals, pricing, anything that's antitrust related. And the discussion needs to focus on technology. Otherwise, you're going to run into problems.
Nobody was saying that we would focus on pricing, right? So I agree with you, but isn't that not saying the obvious? I'm not sure.
Vineet has an interesting point in the chat. He says share questions, not solutions. I'm not sure you make much progress with sharing questions.
I agree. So I think most people know that I was heavily involved in this 1838 standard, right? It took me 8 years of my life, and even a federal court case I got on my record, right? Because of that. So Srijit, do you have some? Do you want to talk about it? Do you have specifics? Should we set up a separate meeting on what you're missing? Obviously, if you're an Intel missing something in such a standard, then I'm willing to listen, right?
Yeah. So, for example, I listed a list of features that we want to build into this test.
Mm-hmm.
What Phil says that the next, what DFT features I need to do my next level of tests. If you walk down that list and we agree on, how to use the standard, I have no issue with that. So I'm not saying that, 1838 is not a good standard.
Mm.
I think it needs to be articulated how we use them. Okay. Maybe it is already there.
Okay.
And I think that really needs to be the next level of details. It's not for me to say there is no standard and we cannot use this standard. Let's articulate
sure.
how. Yeah.
Can we?
So maybe you want a specific example case, right? See if we can do it in the standard.
Or if you can abstract it, if you can abstract it, that's fine, right?
And maybe if it turns out that it cannot be done in the standard, then we have a clear case that we need some extension, right?
Or we need extension. Yeah, I think that's the discussion that needs to happen. Yeah.
Okay, good.
Yeah, I think that would be a great discussion to have in the future. And that was one of my questions was, how would we even go about forming a standard bodies or getting to the point of that discussion? It sounds like maybe we have that already starting here. Sridhar, and question maybe starting with you and then opening up to anyone else. What particular things would you standardize? So if you have one chiplet talking to another, you have many signals going from chip to chip. Would you things like standardize, I need this eye opening, I need specific voltage swings? What things in your mind?
I think there are a lot of things, right? For example, design by itself clusters these signals, right? Internally within, say, Intel, I can go cluster 32 signals with one clock, right? And then have all the chiplets do that. But do we need some standards across the thing that then these are the kind of clustering we do. This is the kind of test patterns we need, right?
Yeah.
This is the kind of diagnostics features we need. This is the kind of clock control we need. We need to get down to the weeds and then go through this list. I from my experience, I can give you a list, but I'm sure others are facing others, right? Make a comprehensive list and let's, the UCI Express, that was the, I provided some feedback, but all of these standards that are coming on board really needs to look at what we need and clearly articulate how we are going to implement.
So what you're mentioning.
So I mean.
What you're mentioning, like groups of 32 signals with a common clock.
That's one example. That's one example.
So I think I will be able to do that right now in the FPP of the flexible parallel port of 1838, right? And I think.
But we are talking about through the DWR, right? Now the FPP, right? So we'll have to focus on the DWR part of the standard, okay? And that's what we are talking about.
No, but the DWR is just saying there's some functional interconnects, right? And so the standard, of course, doesn't interfere with what should be. So
those are the functional ports that I'm talking about testing, right? I have 100,000 of them. Remember, these are all.
Okay.
Yeah. That is the part that I think is missing from the document in 1838. Today it is 100,000. Some devices are smaller, others might be much more, and I can see more coming in. And we cannot, as I mentioned, we cannot rely on system level test. The numbers are too large, the defects are too complicated, and we need a lot of support. It's almost like we have another cell-aware based testing methodology for this interconnect that we have to develop and support, almost, right?
Dave,
and throw in the complications of clocking and all that.
Yeah, Dave, did you have something to say?
Please.
Sorry.
Standards are fine. Standards are a great start. They don't go far enough, people. We need a file format that depicts, encompasses the standard. We need a way of communicating in a standard mechanism, a file format, to allow those voltage levels to be translated automatically and consistently into a test program to allow the vectors. So standards don't go far enough. That's my message.
Mhm.
And sorry, Zoe, can I jump in
Oh,
to
yes,
build
go
on
ahead.
what Dave said? Is I think the first question is, let's say you're the final integrator. You're getting all these chiplets. What do you need? I would say I want to be able to duplicate all the tests that the chiplet provider did at Wafer Probe. I want to redo all that. And even starting at that basic comment, I think today chiplet providers would say, no way. I'm not giving you all that stuff. You know, here, run a little BIST and we're out of here.
So why is that, Phil? Why don't they? I know this is from where I see this has been a long question I've had to, and suppliers.
If I were a chiplet provider, I wouldn't want to do it either. It's a pain in the butt.
You want to do that?
These guys, they're going to ask 1,000 questions. They're going to stick their nose into my business. I don't want to share all that. And actually, there's some use cases like with high-speed analog to digital products that need to be recalibrated at the final package where there's no excuse. I mean, you have to be able to redo that. And so that's one. I think the simplest case is this HBM JESD 235. It's documented. It does a lot of stuff, doesn't do everything. Zoe, it comes back to something that I know you're very passionate about, and that is what data are you going to get? How is this part tested? What's the lot? What's the wafer? What's the parametrics? Do you get any of that data or not?
Yeah, so actually that brings me on to, I look at a question here by Harry Chen, and he says, would component suppliers be willing to share chiplet health data? So he's taking it one step further. Health condition data provided by embedded monitors in order to diagnose a system level fail. So I think the industry is at a big point here where we're getting a lot more of these on-chip sensors and monitoring that you can really see what's going on a lot closer in the silicon than we've used before. And with AI and machine learning, we're now doing a lot of analytics on that to really see which chips are marginal, predict future failures. Do you see that as something that's going to really take off in the industry, and suppliers would be willing to feed forward, say, information on a chiplet?
Yeah, so I think that depends, you'll get what you pay for, right? I remember, for example, repairable memories. Of course, they're maybe not so good as a memory that was, right from the get-go, right? So if you have your own pacemaker, maybe you prefer to have it with a not repaired memory, right? But that comes at a premium price, of course, because the supplier, if he can sell both the repaired and non-repaired memories together, then that makes it easy. So if you want only premium memories that are not repaired, you have to pay for it. If you want to have the test data for, So I think how to do that is known, right? So there's no technical challenge anymore. It's just a business agreement that you need to set up. And then Al will say we should not talk about price and business here.
Zoe, Phil touched on soft data errors.
Yep.
And I think, that it reminds me of alpha particle errors in the memory industry years ago. And at that juncture, memory vendors were really careful. They didn't want to say they had a problem, and they didn't want to share their data. In the end, it ended up being a fundamental problem that people could address. I'm not sure soft data errors are going to be that. I think we may need to do what Harry suggests and share this empirical health data on our chiplets, especially if parts age.
Right, that's right.
And sorry, Dave, let me jump in. I talked about silent data corruption. My experience has been so far, those are not soft errors, that they may be more random defects that are just very subtle. And Zoe, I'll shut up in a second, but go back to Harry's comment. One interesting things these monitor gives is, in theory, they're going to be measured at all levels of assembly, including in the field. So it's not like as a chiplets provider, I say I'm not sharing it. It may be that both the integrator and then in the final system, they're measuring the same stuff also.
Right, that's right. Yep.
On that point, these are devices that are monitors that are put on the chiplets, right? Maybe the industry could agree on what kind of standard monitors we will put on the chiplets, right? That might be the way to go, rather than, Yeah,
that's a good point, isn't it? What monitors, but then you can put any monitor on there, but then to me, it's the reading out being able to read out that monitor and then understanding what the data is to do your analytics. So to me, that's the coopetition part, isn't it? That whoever you might buy an IP that is the agent, you put the agent in the chip, and then you want to read that data out. But when you read that data out, you need to understand what those values are telling you. So that, again, that requires even more coopetition.
That's true. Yeah.
Are we at the stage where everyone's prepared to open all that up? Because it's really like sharing your dirty laundry, isn't it, to some degree? Are we there yet?
Yeah, so I think if you have one, I don't know if they exist, but if you have one fully vertically integrated company that does everything by themselves, then it of course would be easy, right? If you don't, assuming that you don't have, department against department fights, right? But the more the industry gets chopped up in different things, you have these boundaries, and then I think it only works either if it's in standards or if you have a very tight tight cooperation between two companies. So if you have one supplier that is fully dependent on a certain customer, then of course they're willing to keep them happy and provide that. If they have many customers, but you want to be the special customer that get all the test data from them or the health data, then still what I say, you should pay for it, right? Otherwise you don't get it because it's extra work for them.
Doesn't that go against what Al said? He said you need to keep the cost out of it, but I clearly understand that paying, you get what you pay for.
No,
but
I think Al is saying that for standardization, right? If you set up a standard, you should not talk about cost. If you set up a standard, you should not talk about cost. But if you do business, of course you talk about. You go to your supplier, of course you say I'm only willing to pay so much and not more, right?
Eric, I think you're an example showing how the speed of innovation is driving the need for multiple vendors. In fact, you're an enabler for all of this. So, I mean, I would posit that we can't not work together in the future. I mean, Intel, TSMC, Samsung, Broadcom using Samsung HBMs, although Phil didn't want to admit that maybe in the future he may want to use some Intel IP or something like that.
What helps us, of course, in our business is that the cost of the next generation technology, let's say, is every time more and more expensive, right? So there's more and more people that say, I cannot afford this any longer to do it by myself. I still need it, so let's work together with the others.
I guess, back to my original question, what won't happen? I think where the limit is we will work together as long as our end customers demand it.
I think that's an excellent point there, Dave. So we see, in the OSAT industry, of course, with advanced packaging, we see a lot of that could be driven by our end customer. That end customer would be either identifying or actually supplying those individual components from multiple vendors. Typically, those end customers would want to have the most control over what information is passed. They would see it proprietary to what suppliers are choosing and what functions they're asking for on those particular chiplets. And from the OSAT industry, especially on advanced packaging, when there's a defect of some type inside a 3D package, trying to figure out if the advanced packaging piece is a part of it or if it's the actual known good die that's a part of it. That's very interesting, especially when it comes down to commercial negotiations on yields and such. That's, of course, difficult for someone who might be doing testing either at the final test or SLT phase. So I see that, our industry is a living, breathing thing, and it will continue to morph. And we talked a little bit about what we are today may not be what we are tomorrow. I always like to use the example of the foundry business where, years and years ago, they were just supplying processes. And now they're supplying IP that can be reused by their customers directly. And they weren't doing that 20 plus years ago. They were learning those particular, memory IP or high-speed serial interface IP. So what we do today, I can guarantee will be different than what we do tomorrow. as all of our interactions grow and change. But thanks, that was a good point, Dave.
Yeah, I think you bring up a good point around, TSMC or fabs supplying IP, and, OSATs do so much in terms of writing test programs and providing test capability. Do you think that fabs and OSATs could do more to ask their suppliers to provide more information as a third party, saying, hey, you supplier, you need to provide this information to this other customer of ours because this is where we need to get to? Do you think that you have a role in actually making other people share information more quickly?
Well, I do. So whenever in the industry, I see a team come together trying to solve a problem, people will always say, oh, it's this test engineer from this company or this particular IP or this particular block that's responsible for driving the solution. I don't think so. We have all different personalities, and some personalities are better set to lead a team to drive to a certain solution and get the collaboration from all different parties. Because usually some of these very, very difficult problems, some that Phil were discussing, will take a number of people just to eliminate usual suspects or eliminate suspects and getting their collaboration. So I think anybody that is trying to solve that problem to improve the productivity of the cost and the performance, and also the whether it be reliability or quality for that product, anybody can try and lead the team to get that team to come to a good solution, a good resolution. And maybe it's just eliminating suspects. Maybe it's actually getting to the root cause. So yeah.
I guess as you're talking, something came to mind around, we call it concurrent engineering. And I know the earlier a DFT team or the test team can be involved at the product inception to really define what's required helps. But often that's an afterthought in companies. But I think we as test engineers can do more in our own companies to proliferate more DFT and more data out there that can be used because we're the ones that will be preempting what's going to fail at the end, and we will be the ones that are debugging at the package level, trying to figure out which chiplet failed. And the earlier we are involved in design, the more it will benefit everybody.
I talked quite a bit about this last time I presented. I think it was back in October. I think one of my last slides showed where the test flow, starting all the way back from the components that are tested in line at the wafer fab for discretes on sheet resistances and contact chains, all the way through the let's call it the final test and the final test and SLT phase before it got onto the system board. I was showing how a product that may not have had burn-in ever needed will eventually get burn-in if it's in a package that needs to be burned in. Understanding how that particular device was tested previously, right? If it was already burned in elsewhere, it might, you might be losing lifetime later. If you don't get that information from the supplier, you wouldn't know that. You might need to get, detailed device physics information about how much you can stress it, and they may not be willing to disclose that. So a lot of fun stuff there.
Zoe, I mentioned the collaboration between Intel, TSMC, and Samsung, and I was thinking about what caused that to happen. And I think there's a cost pain threshold. And in that case, it might have been the cost of fabs and tools and the like. And I think in terms of, the OSATs working together, if their customers have a cost pain threshold that is better achieved by working together one way or another, I could see barriers being broken down. So to me, that's the fundamental reason or a way that this gets enabled.
You're right, Dave, and you mentioned 3 companies there. They're all 800-pound gorillas, so maybe they sort of met mutually head on. Do you think companies might withhold information? The smaller gorillas in the room would maybe hold information. or I'd say companies, to unbenefit potentially competitors? Do you think that might go on in the?
When the standards work, I mean, obviously pre-competitive collaboration.
Yeah.
And pre-competitive is the key word there.
Mm.
Once I get the thread of something really cool that could benefit Advantest, certainly we're not going to be sharing that. So I think naturally that happens. I don't know what I'd be curious what CG feels from his efforts in the standards work. Or Phil.
Well, I've not been that closely involved. Obviously, would like to be involved in the standards work because I've been, inward facing. What I see as our business growing, and we are trying to integrate chiplets from other vendors. I think this is going to become a growing need for us.
Yeah, and Dave, my rule of thumbs always is, I want to talk about things I don't know about or I'm not an expert at. If I really know something, then that's why. And Zoe, one question, actually, I don't know if this is allowed, but I have for you is, you're buying a chiplet. What data do you want from the chiplet? And probably more importantly, what should be standardized about the data you get from the chiplet? For example, serialization for the kind of at least high performance or advanced technology, everybody ought to be serialized. What other data should be required? And should there be an industry standard about that as you buy chiplets?
Yeah, so Phil, that's, that I always think about that in my day-to-day job. And back to your point around, we want to run everything. Yeah, so if we buy a chiplet, we would want to run all the DFT from that chiplet at our next level of integration right through. Yeah, so particularly if I have a chip-to-chip interface, I'm going to want a specific DFT to run over that interface, and I'm going to want to be able to fault isolate if any particular lane fails. I need to fault isolate which lane, because I need to know why. Is it a random thing? Is it something systematic that's going on? Is it because the chiplet was slow? So I wouldn't just want DFT if they were on-chip sensors. I would ask for all that information on the sensors so I could run sensors right through the whole end-to-end test flow.
So let's say today, chiplet providers won't provide that. How should we help the industry evolve? Would it be a standard, best practices, or do we just let these 800-pound gorillas get what they want and everybody else is just left for,
I think,
the scraps?
Standards
you get
help.
nothing.
Yeah, standards I think always help because you can ask the supplier to test to a specific standard. I think even when you have fabs and OSATs involved, definitely have a weight. If TSMC says, if you're buying this IP, putting it in your chip, then you need to let this IP run for your customers too. Yeah, I think fabs can definitely have a big say here. They're very influential, especially a fab like TSMC. Is in a big position to do that.
What data do you want? Independent from what tests you run, you're getting a chiplet. Do I get any data besides serialization or not?
Yeah, data, any DFT data. Yeah, if you're running any PRBS over an interface, any traffic patterns over an interface that are generated on chip, I'd need to run all those tests and gather all that data. What failed, what lane failed, how did it fail? Was it high, was it low, was it a closed eye? If I have agents on the chip, I would want to run all those agents at all subsequent test steps and things like that. So basically,
but as a chiplet provider, I might just say they passed. There's your data.
Yep. Then it becomes down to negotiation. Maybe you get what you pay for, Eric Yarn's point. Yeah. Maybe you have to hit the wall with low yield and major issues to get the supplier to open up. There's many avenues you can try. You can beg, plead, and I don't know, whatever it takes. Yeah, but it's true. Some companies will only give you, particularly memory. Yeah, they just give you the black box. It works. And then it takes a lot of engineering resources to figure out what's wrong and convince otherwise.
But to jump to the chase, should HBM providers provide more? For example, Harry asked about some quality metric related to yield and other things. Should they be providing that for each HBM provided?
You want me to answer? I became a panelist. This is fine. So my quick opinion on that, my 30-second opinion. I think yes, because I love looking at data because I'm a data person. So from the technical side and interest side, absolutely. From a business side and being able to maybe re-annotate yield and things like that, I absolutely understand why things like that don't happen. So that's my quick answer. Would anybody else like to answer?
Again, I would push the envelope and say, that's easy. What about, marginal bits and, sparing algorithms and. I mean, it's a slippery slope. And I don't know how to answer this. I guess how I would answer it is, we're not sharing enough today. Now, where can we go next?
Yeah. I agree. Okay, we only had one question from the audience. I think we need to wrap up the panel in 5 minutes. If there's any quick final question from the audience, please type it now.
And Zoe, I'd like to ask a question of the panel. Years ago when I was the board test engineer, the company that made the tester published all the defects. And so as users, you knew what the problems were. And so other users, when a different user found of an issue, you knew about it too. And then they changed to a closed format where they wouldn't tell you what the defects in the tester was. So similar to the open source world of software where people were publishing the bugs, do we see anything like that going to happen in the chiplet space where multiple users of a chiplet can at least compare notes and learn what issues may be out there or what issues may be impacting there? Or do we think we're going to stay very closed where everything is secretive between the chiplet supplier and the customer?
Anybody like to take that?
I assume you mean defects in the chips, not the testers, because I don't expect tester defects to be shared anytime soon. But
there are none, Dave. Come on.
Well, actually, Dave, one of the #1 requirements we get from customers is test version. So it's not a defect from the test equipment vendor, but it's the test program version.
Well, and I would comment that time since cal is a key parameter that a lot of people consider critical and should be available and potentially shared. But
don't say that to our customers. We don't have that.
Yeah, me neither. Well, I do have it, but anyway. Zoe, I think it'll be a long time before we can share defects per chiplet. Although I think, honestly, my comment on soft errors, I think we're going to have to get there. I don't see any way around it.
If you look at a 3D stacked IC, right? If you look at it as just a different shape of a system on chip. System on chip, of course, everything was manufactured by one guy, right? There's a C manufacturer. So then he knows the yields of all these things, right? So of course you get the core from ARM or wherever you have core providers from. And I remember when I was at Philips, we did do the tracking that one core maybe had more defects than another. And even though it was the same technology, so then you could quickly blame the design, right? And then so it's all possible, and I don't see why not. But obviously the die providers they don't like it, so you have to pay them extra before they're willing to do so.
Let me throw out another example, and this is a reason why it won't be done. I don't know, it's probably 10 or 12 years ago in one of the x86 processors, there was a math error that only showed up if you multiplied 2 to the 15th times 3 to the 22nd. And Intel actually did a change order, a design change to fix it. I suggest that those exist today in a lot of our devices. They're unknown to anybody but the manufacturer and maybe not even them. And I maintain that we're not going to be, there are limits, and we won't be seeing what Intel did in the past ever again.
I'm not sure we are talking about that kind. That was, if I remember the history right, there was a verification error. So there was a design problem. It was not a manufacturing thing. What I think everybody's asking is for manufacturing defect data. It is extremely difficult, even within a integrated company like Intel, for the design team to get the defect data. It's a thing. So I can imagine the difficulty in actually releasing them to outside vendors. So
Sridhar, let's say I want to buy an Intel chiplet 3 years from now. I don't know what, your new GPU, and it's just a chiplet. I mean, what test information and test data do you see delivering?
I don't, actually, that's a good question. What do you need? I mean, that is the thing. In my opinion,
I need it all. I need everything.
Yeah. So, and the question is the business agreement there that they will provide you with everything or not, right? I think that is really the thing. We obviously have all the tests, right? We run it in our manufacturing, and
But Sridhar, within this technical community, we ought to talk about technically what's required. And let the business people deal with all the business stuff.
I agree with you.
So what do you think technically is required?
Oh, I mean, for me, just off the top of my head, I would need all the tests, at least the final runs in the class test, right? So,
do you think it will take individual companies to write up individual contracts on what is needed? So it will always be one-to-one between two companies in a private contract?
I think that is what would be the first step. I don't know if you can get an industry-wide standard to make that as the collaterals that you supply, right? So that would take a long time. So
yeah. Okay, I think we're just about at the end of the time here. We're at 10:30 Pacific time, and we had a really good chat. I think there's just so much that can be said on this topic. Would each person give your 30-second summary of? I almost want to say, I do feel like that you can help your company do more coopetition going forward. Has that spurred you on? Give me your 30-second reply, please, to wrap up. I'll start with Eric Jan.
Okay, thank you. So I think the competition, I see that definitely happening, right? Also for testing, the joint product. But I think at least you will need, I think in 3D stack testings, you want to be able to test your die still after stacking also. Because, for example, the thermal compression bonding could damage some of them, right? And therefore, and you don't know what is inside these dies, and you don't want to know because that is too much. So you want to get the test from your suppliers. And so I think that is something, very useful, and that is what people will be able to pay for.
Yeah, very good. Thank you. Sridhar, would you like to?
Yeah, my main message would be, let's work on standards. I believe that there is a gap in the standards for the interconnect testing, which is becoming very important. So whether it be shoring up the 1838 or some other standards, let's work on that. Yeah.
Okay, thank you. Phil?
So we just had a good discussion about data sharing and method sharing. So I won't bring that up again. But to me, one of the most interesting things is to understand, let's say, challenging failure mechanisms. For example, we haven't discussed it enough, but what's the role of SLT? Why do we need SLT after AT? What does it detect? Does it find what are silent data corruption fails, and how do we find those? And that's one of the most interesting things I think we can talk about in the industry.
Thank you. Al, give your 30-second position, please.
Well, I hope you guys go down the standard approach. That's the only way I think you're going to find some, leveraging everybody's technology.
Okay, good. Sounds like we need to do the standard thing. Dave.
I was very enthused by this. I think the opportunity is here for a faster data conduit from the tester, for on-die sensors with data on them, and for files that are shared through multiple vendors along the way that standardize how we look at things and use it. I can see us going to the next level is the bottom line, and I'd be happy to to explore that with
Great
people.
goal. Yeah, thank you. And George.
Hey, thank you. You know, like I said before, Coopetition is here already, and I really strongly urge all members of our community to continue to find ways to cooperate together. The more we hide, the more it's going to hurt all of us from that fear. I think the more we learn, the more we share together, it just enables the industry to continue to succeed and be the wonderful industry that we're in today. So I just continue to urge everyone to be as open as you can about what you're doing, what you have, that will help everyone have more productive, more safe products for our customers.
More cost effective too, I believe. Very good, thank you. I'd like to thank all 6 panelists. This was a great discussion. I felt that we could have talked this all day over a beer. Yeah, maybe one day we'll get to do that. So thank you very much for your time. I hope the audience enjoyed that, and I'd like to hand back to Ira.
Thank you, Zoe, and thank you all the panelists. And then lastly, I want to thank our sponsors again. Our diamond sponsor, Omcor, with differentiators in technology, quality, and service. And Advantest as our Emerald sponsor, receiving the highest ratings in the annual VLSI research customer satisfaction. And lastly, I would like to thank all the presenters, the panelists, and most importantly, everybody who attended that made this a great event. And I look forward to seeing you at a future event, either here online or in person. And I will wish everybody a good rest of their day. Thank you.